If you want to see a black hole tonight, just look in the direction of Sagittarius, and there's a raging black hole at the very centre of that constellation that holds the galaxy together.
Whoa!
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Deep space. Who was that, Matt?
It was Michio Kaku, world-famous quantum physicist and science advocate.
He's got great hair as well, hasn't he?
I absolutely love Japanese hair when it goes grey.
They've just got the coolest hair. You know?
They actually do, aren't they?
I might get
Really
I might get a Japanese wig.
I think secretly you're turning Japanese.
I really think so.
Nice.
Matt, we're going to talk about something we're both quite geekily excited about for once.
Everything I knew about black holes is wrong.
So, listeners,
I'll start with that.
Just to put it into perspective,
Yeah.
a couple of weeks ago, Matt, as you know, we prep hard for the shows. Matt said to me, "What do you want to?"
We're prepping hard.
Anything you want to discuss for next week's podcast? And I said, you know what? I'd like to discuss black holes because I don't know much about them other than one of my favourite space sci-fi / horror films, Event Horizon. And
yes.
I'd like to learn more, Matt. So
before we fall into a black hole, let's just quickly do the space news.
let's bash it out.
We're recording this very early this week.
Yeah.
For work commitment reasons. So
I like that.
So here goes. Space news. So in a world first, an ESA-led team has built and fired an electric thruster that's able to ingest air molecules from the top of the atmosphere.
What?
This is really cool because this means, for example, there was an ESA space mission quite recently called GOCE, or GOCE, Gravity Mapper. And actually, that's the gravity mapper where you see these brilliant pictures of Earth and how the gravity is actually...
I think I've seen that. That's a really cool looking thing.
It flew for a few years, but its lifetime of that particular satellite was limited because it's always working against the drag of the atmosphere. And so it ended up using its 40 kilograms of xenon as a propellant. Once it was used up, the mission was over. Whereas this new breakthrough means that you can have these satellites flying in the upper atmosphere at about 250 miles up, 250 kilometers up, I should say. They're sort of sucking in through a special intake the molecules up in the upper atmosphere and able to accelerate them through the electric thruster, obviously using solar panels as the electricity supply, and therefore you've got almost an unlimited supply of propellant. That
could be quite revolutionary.
Yeah, absolutely, and you could do it on other planets as well. So you could use Mars's carbon dioxide atmosphere. It doesn't really matter what you're forcing through this thing.
So wait, Matt, are you telling me that this could be a new way that we fuel space travel?
Fuel satellites. Yeah, fuel satellites for long-term duration missions in very low orbits.
Right, so this couldn't be anything to thrust humans in rockets?
No, absolutely not. These electric thrusters, because they've got such a weedy amount of thrust, really, they're completely useless for that. But they're very, very good for station keeping and stuff like that. So,
Matt, if we were going to be in a thrash metal band, would we be called Electric Thruster?
We are, aren't we? Are you advertising our latest single?
Out now. Oh, go from HMV.
Here's a quote. This is how important it is. ESA's Lewis Walcott said, "This result means air-breathing electric propulsion is no longer simply a theory, but a tangible working concept, ready to be developed to serve one day as the basis of a new class of mission." Do you know his previous job was that of a 1950s news presenter?
Yeah, it's brilliant. It's like Monty Python, this podcast at the moment.
Right, so what's next?
Well, I think we should talk about Lightsail 2.
Yes, so there's a date on it. There's a date on Lightsail 2 going up.
Get out of town.
Yeah. Remember, we had Harriet Brettle. The first time she came on the show, she was talking about Lightsail 2 because she was representing the Planetary Society here in England. But yes, it's going up. On which rocket is it going up on, Jamie?
Well, it's only FH, isn't it? Falcon Heavy.
It's the big Falcon Heavy. So it's going up. The Air Force have this thing called the STP, which is some science payload that the Air Force sponsor, and and this is going to have lots and lots of different spacecraft on board. The STP-2 is 25 small spacecraft, including Cosmic 2, a cluster of 6 satellites, 8 CubeSats deployed by Peapods, Lightsail carried by the Prox-1 nanosat, Deep Space Atomic Clock.
Deep Space Atomic Clock. You're making that up.
I'm not. So Deep Space Atomic Clock's going up.
Matt, did we say when it was going to be launched?
Sometime after June the 13th, so a 60-day or 2-month window.
Matt, do you, even though I know we're both rational men, if you were going to have a choice to launch on the 13th or the 14th, would you like me go for the 14th?
I'd go for the 13th because it's an opportunity
to prove people wrong.
All wrong, yeah. Absolutely. I know what you're saying.
What I'm saying to you, Matt, is that I still don't walk over 3 drains if I can help it. Because when I was at school, a girl called Carla told me that if you walk over 3 drains, it's bad luck.
I don't tread on the cracks in the paving stones either.
You're a crack dodger, are you?
Just in case the bears get me.
Oh dear!
Very
silly.
Well, let's quickly get through this.
That's amazing.
Let's quickly get through this news so we can talk about black holes, Jamie.
Yeah.
Right, here we go. So, British astronaut Tim Peake,
our mate Tim,
has been visiting Airbus in Portsmouth because he wanted to look at the new Eutelsat quantum satellite.
Woo!
Yeah, so that's being manufactured by Airbus and Surrey Satellite Technology Limited. And it's the world's first geostationary telecommunications satellite that will be fully reconfigurable in orbit. So once it's up, you can program it from the ground to do any type of communications task, which I should imagine is quite revolutionary. Although I am slightly disappointed that it's not actually a quantum satellite like the Chinese put up.
Yeah.
I think a better name or a less misleading name. It's almost like clickbait again, that quantum satellite.
It really is. Well, that's amazing.
But no, it's still amazing. And Tim Peake's obviously flying the flag for that particular fella because ESA have put a lot of money into that as well.
Matt, I haven't had a text from him saying that he was coming over. Have you?
No, actually, he didn't.
I must have just given him one wrong digit.
I even said I'd make him a nice cup of tea.
Yeah. Gross. What else?
Bridenstine.
Blocked
again by the Senate. So now, in its second year, NASA without a permanent leader. Apparently the Obama administration were adamant that that shouldn't happen, but the Trump administration aren't so bothered that they've left NASA completely rudderless.
What a surprise.
Don't you think that Bridenstine sounds like one of those conflations of Bride of Frankenstein?
I was just going to say it makes me think of that. Yeah.
Yeah, it's weird, isn't it? We got a few launches that happened. Atlas V launched a GOES 17, which is the second of the next generation weather satellites, and the pictures off those things are incredible. So the NOAA, NOAA, not the biblical boat captain.
Yes. Let's just state that now.
The National Oceanic and Atmospheric Administration. It's one of their satellites, and these things, these new versions, should be up flying around doing weather forecasting and meteorology until 2036.
Get in.
They're made to last, these things.
Well, that's very cool. The next time you have some dank snow, it might be told by that guy.
Mm-hmm. Falcon 9 is going to launch a Hippasat 30W6, or was known as Hippasat 1F.
Rolls off the tongue.
A Spanish comms satellite. And I noticed actually that satellite is powered by 4 SPT-100 plasma propulsion engines by the Russian OKV Falcon. And that's a Hall effect ion thruster, much like the ESA thruster we heard about earlier on in the show.
If I was going to choose any engine, it would definitely be the plasma propulsion.
Yeah,
just
I'm
saying,
going
Matt.
for plasma propulsion. Yeah,
people know me for that.
Vasimir should be your favourite because it's by Franklin Chang Diaz.
Great name.
Anyway, black holes, Jamie.
Here we go.
What's your favourite black hole song before we start?
It's definitely Black Hole Sun by the incredible Soundgarden.
Mine was that until I remembered it's Black Holes in the Sand by Gravenhurst.
Which is amazing, but not as good.
They're both brilliant, but both a different kind of listening experience, aren't they?
Both very good. One slightly better than the other.
Everything I knew about black holes is wrong.
Surely not everything.
And no, everything. So Wikipedia, the very first line it says, which is what I thought, a black hole is a region of space-time exhibiting such strong gravitational effects that nothing, not even particles and electromagnetic radiation, such as light, can escape from inside it.
Whoa.
Now, see, that is what I thought, but if you were on QI, the Stephen Fry comedy vehicle, that's the sort of thing that would get you the klaxon at the end, sort of flash up behind you. The reason why light can't escape from a black hole is not quite the fact of gravity. It's because the space-time curvature is so extreme and weird that every direction is inwards.
What?
You can imagine it like a weird video game where every direction you go will always lead you to the centre.
Right. God damn.
So let's have a little bit of history of black holes. Ready?
Let's bang it out. Where are we going to start?
Obviously, black holes come out of... Originally, were just a sort of mathematical quirk that fell out of Einstein's general relativity. So the first modern solution of Einstein's general relativity that was a black hole was found by Carl Schwarzschild. Now, remember that name because his name props up quite a bit. In 1916.
Right.
But objects whose gravitational fields are too strong for light to escape... But you can imagine a planet that gets so heavy that the escape velocity is higher than the speed of light.
Okay.
An English clergyman called John Mitchell, who was a little short man of black complexion and fat.
That's not your words.
The only description of him, there's no photo of this guy. John Mitchell, in 1784, was the first person to really think about this type of object. So the first interpretation of a region of space from which nothing can escape was first published by David Finkelstein in 1958. So really, that's the first proper black hole description, 1958. So these things have only been theorised for a few years.
Black holes were long considered a mathematical curiosity, and it was during the 1960s that theoretical work showed they were a generic prediction, of general relativity.
So, the discovery of neutron stars, and we'll talk about these later on because neutron stars are part of the story, made astronomers think again and think, if neutron stars are reality, maybe these black holes are as well.
Well, this is very Spinal Tap. Very Spinal Tap. Are you ready?
Yeah.
So they're so hard to see because they're literally blacker than you could ever imagine black.
That's right.
The Event Horizon Telescope, the EHT, however, run by MIT's Haystack Observatory, is an attempt to directly observe the immediate environment of the event horizon of Sagittarius A, the black hole at the centre of our galaxy, the Milky Way, and to produce a silhouetted image of it. The first such image may appear in 2018.
So we might actually have a picture of a black hole this year. This is actually very, very exciting.
Will it just be black? When you say a picture...
They're so weird, Jamie. They're so weird. You wait until we actually get onto some of this weird stuff about black holes. The EHT that you were talking about, the Haystacks Observatory, named after the famous British wrestler, Giant Haystacks.
Yeah.
Of course.
Of course.
Managed to detect magnetic fields just outside the event horizon of Sagittarius A. So these are the things we've actually started to observe. Not actually observe black holes directly, but infer their existence almost beyond doubt. So
Got it.
It's now widely accepted that not only do black holes exist, but nearly all large galaxies have them at their centre. Not only a black hole, but a supermassive black hole.
Right, so the black hole at the centre of every galaxy, its size is dependent upon the size of the galaxy itself.
No, actually it's not. Weirdly, there are some galaxies, small galaxies, that have massive, super massive black holes at the centre. But there is a correlation between the mass of the black hole and the galaxy's bulge, and so it's complicated. I mean, these are the sort of things that are well beyond the scope of Matt and Jamie of the Interplanetary
Matt,
Podcast.
you know that we can take this.
We'll take it on. Maybe someone doing a PhD can let us know about what is the correlation between the mass of the hole and the bulge. So please feel free to drop us a line.
I found it really hard not to make a silly joke. I'm trying to cut down on silly jokes. What am I going to do with that? What am I going to do with that?
I'm going to hit you with fact number 1.
Here we go.
Gravitational time dilation.
GTD, yeah.
So if you, Jamie Franklin, were falling into a black hole,
yeah,
it would, it would be going sort of normal speed to you. But for me, it would look like you're doing everything in slow motion. I go, why is Jamie doing it so slow?
Whoa.
So the consequence of that is if you did go to a black hole and stayed there for a bit and then came back, you'd be millions of years into the future probably when you came back to Earth. And of course, Interstellar, the film, played on that theme loads.
Yeah.
It's true near any gravitational object. So atomic clocks on GPS satellites will get milliseconds ahead each day. If you don't take that into account, GPS actually stops functioning. So they have to take that gravitational time dilation into account.
Oh, I'm spinning out already.
And it's just to do with the mass of the object. So if you were by a massive object, your time is dilated. Time seems to go normal for you, but seems to go very slow for someone observing you.
Got it.
Right?
Wow.
This is fact number 2. As an object approaches the edge of a black hole, or some people call it the event horizon, and we'll find out why it's called the event horizon, then they actually freeze. They appear to be frozen in time at the event horizon. Not just for a bit, but forever. Even if you were immortal, they'd be stuck on the edge. They would freeze at the event horizon. But to the object,
right.
But to you, Jamie Franklin, as you were falling in, you would just have crossed the event horizon and as if nothing happened. So once you fall into a black hole past the event horizon, if you were able to look out, and this is how Neil deGrasse Tyson puts it, you will see the entire future of the universe unfold in front of you in a matter of moments, and you will emerge into another space-time created by the singularity of the black hole you just fell into. So the important bit is, as you looked out, you'd see the entire future of the universe unfold in front of you.
Oh, God.
It takes you to the end of time. That's how weird the singularity is, right? So events beyond the event horizon to the object happen, but to observers outside, they don't. And that's because events inside the black hole have no when.
Okay.
The black hole is all these events that happen within the black hole, but we delete them from our self-consistent history records. To us, they don't happen, even though they do happen. It's the thing that that fell in.
Matt, I don't know where to start with my questions.
And it's not because we can't see them. It's not like a curtain has been drawn over the event horizon. It's not that. It's because events can't happen after the event horizon. That's why it's called the event horizon. The last event that happens when any single thing enters a black hole is called the event horizon. Time and space are, of course, the same thing, space-time. But they swap round, so space becomes time and time becomes space, sort of. And so the singularity isn't just a place, it is the infinite future. So it's a time.
Oh, God, I want to understand, but I don't quite. I'm just going to be honest, Matt. I don't quite get it yet.
It's not really even an object, but we can treat it like an object. So fact number 3... even though a black hole is kind of not an object, it does have gravitational effects. For example, the sun is a massive object that bends the surface of space-time, just like a cannonball would on a rubber sheet. So you've seen that experiment where you put a cannonball in the middle of a rubber sheet and everything orbits around it, blah-de-blah. And it's a very good description of general relativity. But we can replace the sun in our solar system with a black hole roughly 3 kilometres in diameter, and the orbital mechanics of the solar system will remain unaltered. Obviously, it will be a disaster on the temperature front.
Be a bit cold. Yeah, plants would suffer.
And the same if you replaced Earth with a 1 centimetre diameter black hole.
1 centimetre?
Yeah, 1 centimetre black hole bends space-time in the equivalent way that the Earth does. Yeah.
Whoa. Wow.
Black holes, and this is what a lot of people get wrong, black holes don't suck things in. So it's not like
See, that's what I thought. I thought it was a big black hoover in the middle of the galaxy, sucked stuff in, and when it did, it was just, you don't know where you are
No.
or what's happening.
In
There's
fact,
no time.
If the sun was replaced by a black hole, it's not doing any more sucking in than the sun is.
Right.
Except when you get to the event horizon. That is it. You are now doomed and trapped forever.
So can you see, if you were in a rocket, Matt, could you see the event horizon?
No. Another misconception. So black holes are black. They are black. Actually, you can't see the light on the event horizon, because what's happening is its time has been so dilated that the redshift of the light coming off is therefore so redshifted that the frequency is lower than you can detect. It's kind of like a sine wave that's gone flat into a straight line, so you just wouldn't be able to detect it. So,
got it.
So actually, earlier on when I said an observer would see Jamie Franklin freeze on the event horizon, what would happen is that you would start to slow down, but you would also be fading away because of this redshifting effect.
Would it be like that photograph in Back to the Future when his brother disappears in the photo?
That'd be the freakiest thing.
I quite like that. It'd be like, all right, Matt, don't worry, I'm still here.
This is actually my favourite fact. This is the one where George and our jaws were dropping at this one.
Go on.
It's absolutely genius. So the densities of black holes are not necessarily that dense. So a lot of people talk about infinite density and things like this, and it's a bit of a weird one, because density is the mass of something divided by the volume, right? So a supermassive black hole at the centre of Andromeda Galaxy, so that is 110 to 230 million solar masses.
That's a lot.
So it's a big old black hole, but the volume is so huge that its density is actually less than water.
Jeez.
Yeah, and the consequence of that is a black hole that has has one solar mass. As you fell towards it, you would get spaghettified. So the tidal forces are so strong that your feet are nearer than your head, so would experience a much stronger pull. So it would literally stretch you and spaghettify you.
Oh, Lord.
So that's the tidal forces are extreme round one solar mass black holes. However, a billion solar mass black hole would completely leave you unscathed as you fell in. So you wouldn't feel that spaghettification.
Huh?
Yeah, so it actually wouldn't be that bad.
I like the idea of you falling into a billion solar mass black holes and coming out and going, you know what? Wasn't that bad.
But Jamie, you know you can't come out. That's it.
Oh,
You're stuck on the event horizon forever. Although you're not, you're inside, but you can never go out. And
I'm inside having a good time.
This singularity has punched a hole through the fabric of space-time. And what does that really mean? And no one really knows. Here's a Kip Thorne quote. A black hole really is an object with very rich structure, just like Earth has a rich structure of mountains, valleys, oceans, and so forth. Its warped space whirls around the central singularity like air in a tornado.
That's deep.
Yeah, so inside this thing, there's a lot of geometry and weirdness going on that Kip Thorne is hinting at there. So how are black holes made?
Here we go. We're all sitting comfortably.
So, very large star, and it's burning. But as it burns, there's a nuclear reaction in its centre that is turning hydrogen into helium. Now, very large stars do this really fast, so they don't last very long. Then it's run out of hydrogen fuel, so it then uses the helium, so that gets turned into oxygen and carbon. Then the oxygen and carbon get turned into oxygen, neon and magnesium, then silicon and sulfur, and then finally the silicon sulfur get turned into iron. Now, iron is the end of the exothermic fusion. So when iron atoms fuse together, they don't release energy. So this energy is no longer available to push against the gravity of this enormous, massive star. So the star starts collapsing and causing so much pressure that the electrons get pushed into the nuclei, making all the protons neutrons and make a neutron star. So this thing just gets crushed. So instead of there being atoms made of atoms, it's just made of neutrons that are pushed together. Right. And as this whole thing collapses, the outer cores bounce off this ridiculously dense neutron star in the middle and smash off out into the universe as a supernova. And that's pretty lucky because a supernova contains all those chemicals that we're made from, all those
Elements.
Elements.
My God, did I actually get something right that you didn't know?
Yeah, you did. Yeah.
This is a great day, ladies and gents.
So this neutron star,
Okay.
and we know these things exist because they're seen in the sky as pulsars. So that is the explanation of pulsars. They are these neutron stars spinning away, city-sized stars that weigh as much as the sun. And here is the thing. The neutron star can only exist because of one crazy quantum effect known as the Pauli exclusion principle.
Whoa.
Two fermions, which are the kind of things that normal matter is made from, they can't be in the same place as another fermion at the same time. So when all the places of the quantum realm are taken up, it's called degenerate matter. And the neutrons fill every single gap and have nowhere to go. So they're all stuck in this, can't go anywhere because that would mean they're going into a place where another neutron is. And this causes a thing called degeneracy pressure, which resists the ridiculous gravity crush of the neutron star.
Right.
So it remains a neutron star. So how does it collapse into a black hole? There's a second crazy quantum thing. And have you heard of this one? The Heisenberg uncertainty principle?
Weirdly, I was just thinking about Breaking Bad because we said periodic table.
Yeah. Heisenberg's uncertainty principle.
Circle's complete.
The neutrons are really only a distribution of probabilities. At a quantum level, things aren't in just one. They just aren't in a place. It's a distribution of the probability that they are in that place and what their momentum is and all that kind of jazz. Okay. And this is a real thing. You know, the Heisenberg uncertainty principle is like a cornerstone of modern physics now. At the quantum level, just nothing is what it seems. So if these neutrons are being massively constrained in position like they are because of the Pauli exclusion principle, that must mean that their momentum is highly undefined. You know, you can't know its position and a momentum in accuracy. You can only know one accurately, and the more accurate you have one, the less accurate the other one is. That is the Heisenberg uncertainty principle. Now, this is a way that you can now circumnavigate the quantum effect of degenerate pressure. So as more mass is added, the star actually starts to shrink because it's a quantum object. So as the neutron star shrinks, it gets to a point where the mass is the same as that of a black hole with the same event horizon diameter.
What?
And at that point, which is about 3 to 4 solar masses, or the Tolman-Oppenheimer-Volkoff limit, that the degeneracy pressure of neutrons is just not sufficient now to stop the collapse. And no known mechanism, and I'm going to put this in brackets, except possibly quark degeneracy, yes, quark stars, is powerful enough to stop the implosion. So now this neutron star inevitably collapses to form a black hole. So what happened to all the neutrons inside the event horizon?
This is heavy hitting, Matt. You tell me.
They all get completely ripped apart, smashed to bits. So physics just still doesn't know what happens to all these gluons and quarks as they then get crushed down to the Planck length at the singularity. So that's
Crumbs.
it. So that's the big mystery in physics. What the hell happens at the singularity?
But I love that, Matt. I love that. I mean, what a spin out that is.
Do you want to hear an amazing thing that ties in with last week's episode?
Go on.
At the beginning of the universe, we know that obviously the universe must have been incredibly dense. So how come it didn't turn just into a black hole? How come that didn't punch a hole in the fabric of universe? And it's probably down to the rapid expansion of the universe, or as scientists call it, inflation.
Uh-huh.
Remember we were talking about the Planck telescope seeing this unevenness, lumpiness of the early universe. Well, that lumpiness is enough to create the galaxies. But it's not black holes. But remember, the picture also showed us what the universe was like at 1/9,000,000th of a second after the Big Bang, when it was smaller than an atom.
Yes.
Now, it might mean that those quantum fluctuations in the micro-universe may have resisted inflation and created what is known as primordial black holes.
Yes. Here we go.
Now, primordial black holes, very exciting, because they might not exist. They might be tiny, but anything less than 1 billion tons would have evaporated by now via Hawking radiation.
Exactly.
Those evaporation events, as they finally flare out at the end, might actually be the gamma ray bursts that we keep seeing in the night sky. That actually might be what they are.
Really?
So that's worth investigating. But they might be massive, but still hard to spot. And if they are massive, if they're these massive primordial black holes, they could actually be what dark matter is.
OMG. Matt, have we worked this out? I mean, do you think we're going to get like some kind of award for this?
Yeah,
I'll do some research tonight. I'll look out in the sky, and by tomorrow morning, I'll have written up the thesis.
What you want to do is import some of the Planck telescope data into a spreadsheet, and just apply a few simple formulas and see what pops out at the end. See if you can find any of these primordial black holes.
Well, Matt, you know I love a spreadsheet, and they know me in the Excel community, so I'll have this for you by 9 a.m.
Thank you.
No problem.
But what would happen? These primordial black holes, by the way, could be actually just loads of them just flying around the universe. So there's quite a few effects they could have.
Okay.
They could, if a big one entered the solar system, it could just we wouldn't see it, but all the orbits of the planets would just suddenly get all flung off.
Oh God, that doesn't sound good.
Basically, game over.
Yeah.
They could go near the Oort cloud, and all the comets would start raining in down on us, which may have happened. That may have been what caused
dinosaurs.
The dinosaurs. They might be so tiny that they just whiz through the Earth as if it's not even there, but they would leave a trail of Hawking radiation that geologists might be able to find.
Oh, I love that one. That's cool.
They could be the asteroid mass, and they would sort of fly through the Earth, leaving a sort of tunnel that would go right the way through the Earth.
Yeah, that's going to hurt someone, isn't it, in its path?
Yeah, crazy how. So these things might exist. Primordial black holes could exist, and unlikely, but they could be dark matter. Could be what dark matter is.
Well, listen, we're getting a bit heavy. We're getting a bit dark. I want to lighten things up, Matt. Have you ever heard of a white hole?
No, tell me.
Well, it's obviously the mathematical solution to Einstein, isn't it? Time reverse black hole.
There you go. So you can have a white hole that literally is everything that a black hole does
flipped over.
Yeah, so things inside can leave, but nothing can enter.
That sounds like my soul.
And they'd be unbelievably bright, I would imagine.
Wow.
Space fact, Jamie. Let's finish this off with a space fact.
All right, let's do it.
What is the largest black hole discovered so far?
Well, it's Ton 618, and it's a very, very distant and extremely luminous quasar located near the North Galactic Pole. It likely contains the most massive of all the known black holes, perhaps weighing in, are you ready, Matt? Mm-hmm. At 66 billion times the mass of the Sun.
Mm-hmm.
The light originating from the quasar is estimated to be 10.4 billion years old and shines as brightly as 140 trillion suns, making it one of the brightest objects. I love the way it just says one of the brightest objects in the universe. Astronomers have also discovered the oldest supermassive black hole ever found, 800 million times the mass of the Sun, which formed 690 million years after the Big Bang.
Wow.
In quasar ULAS and a bunch of numbers. Shall I read the numbers, Matt?
Nah.
Don't need them.
No.
Using one of the Magellan telescopes as Las Campanas Observatory in Chile, as well as the Large Binocular Telescope in Arizona and the Gemini North Telescope in Hawaii, quasars like numbers are very rare. I'll read the numbers, Matt. It's J1342 plus 0928.
Which is weirdly,
very rare.
Those numbers are related somehow to your birth date, and the letter J is obviously for Jamie. Isn't that weird?
That's kind of true.
Yeah.
Can't believe it. The researchers searched 1/10 of the entire sky visible from Earth and found just one quasar from this early epoch.
That's incredible, isn't it? So that
How nuts is that, Matt?
it's ridiculous. It is absolutely ridiculous. Black holes are incredible. I love the fact that you have to bring in Pauli exclusion and Heisenberg uncertainty
It's
principle.
just ridiculous. I need to listen back to this to try and make some notes because it's hurting my. I think I probably got about a fifth of that. My favourite thing though, Matt, 140 trillion suns, as bright as what?
That is quasars for you.
I mean, I need sunglasses when I go out in mild sun, otherwise my eyes just stream. Imagine the sunglasses I would need, Matt.
Yeah.
I bet Trump would still look at it.
I think that's so bright that you actually can't see the galaxy that it's in because it outshines the rest of the galaxy.
My goodness. Well, Matt, you know what? I'd love to keep talking, but we're going to have to wrap this up. Guys, I would like to thank you again for your generous donations on our Patreon page. We're loving them. Keep them rolling in. As much as you can generously donate, and this show will just get better. I know it's hard to believe, Matt.
I'm believing
but it will get better. Let's give some shout-outs.
Yeah, so our patrons this week, and this show would not be possible without your support, are Matt Gilliland, Bob Hodges, Richard
Bob.
Swain,
Nice,
Karel
Rich.
Sim,
Thanks, Karel.
Erin Edwards,
Erin, nice.
and the legend that is Julio Aprea.
Oh, yes, we could not do it without you. So, guys, thank you so much. It means the world to us. It genuinely means we can keep doing this, which, you know, I know not all of you want, but we do.
It literally is just brilliant. This is the best thing about doing the podcast. I feel as though you've invited us into your heads. Jamie and Matt, little Jamie and Matt walking into your
Little
ears
us.
from some headphones from some iPhone somewhere in Papua New Guinea. Oh no, it's Ace.
Keep telling us what you want us to cover. If there's anyone you'd like us to interview, if there's a certain subject that we need to get to the bottom of, but please don't say black holes because I don't think I could take it.
You asked me to do black holes.
All right, guys. Well, you have a great week, and we will be back next week.
Thanks so much for joining us, Space Podcasts. See you next week.
Bye, crew.
Bye.
Fly safe.
Bye-bye.